Hello and welcome to the second part for this chapter where we're going to talk about the energy changes in solution, what needs to happen in terms of energy in order for things to dissolve. Right? As you see, all the parts for this chapter are rather short and we're going to move through this pretty quickly. So now let's focus on what's happening in terms of energy in order to get a solute to dissolve into a solvent. So there's three processes that need to happen. The overall energetic solution have three components. I need to separate the solute particles. I need to disrupt the solute intermolecular forces. I need to separate the solvent particles. I need to separate and disrupt the solvent intermolecular forces. And then I'm going to form new solute-solvent intermolecular forces. So those are the three processes that have together. And when I combine those three energy values, that's going to determine or help to determine whether or not that solute will dissolve in the solvent. So the overall enthalpy change for the solution, the delta H of the solution, is the sum of these three terms. Because to disrupt or to form IMFs, just like to disrupt, to break or form bonds, there's an energy associated with that. It always requires energy to break a chemical bond, and we always get energy out when I make a chemical bond. The same is true for breaking or disrupting and forming intermolecular forces. To disrupt an intermolecular force, I need to add energy in, and I get energy out when I make a new IMF. So parts 1 and 2 for this, delta H1 and delta H2, we're talking about the separation or the disrupting of IMFs. Those are always going to be positive values because energy always needs to be put in to make that happen. Delta H3, the formation of new solute-solvent IMFs, is always going to be a negative value. And it's a combination of these three values that will determine the delta H of the solution, whether that value is positive or negative. Right. So the values for these delta H values, delta H1, delta H2, and delta 3, simply goes back to our Coulomb's law again. We said the strength of IMFs is equal to the two charges that I'm dealing with, charge A and charge B in my numerator, divided by the distance between those two charges squared. And we said that we use this to rate to IMF strength, which is related to the enthalpy values. In chapter 11, we used the enthalpy of vaporization, delta H VAP. Here we'll use the delta H for solvation. We're either disrupting or forming new IMFs. A couple things to note, and this goes directly back to Coulomb's law. The closer our ion and dipole are together, the stronger the interaction because that's our R value. That's in the denominator. So the smaller the denominator, the larger my delta H value. The larger the dipole, charge A, the stronger the interaction because that's in the numerator. And same thing, the greater the charge B, QB in Coulomb's law. The larger the numerator, the larger the delta H value. Right? So we're always going to use Coulomb's law again qualitatively. We're never going to put numbers in and solve it, but we're going to use the relationship between numerator, denominator, and how that affects delta H to get an idea of what's going to give us a large delta H versus a smaller delta H value. So like I said, it takes energy to separate the solute molecules. For delta H1 and delta H2, those are always going to be positive. We call those are endothermic values. Anytime you have a positive delta H, that's endothermic. I need to add energy in. I would take energy from somewhere else to disrupt those pre-existing intermolecular forces. Creating new solute-solvent interactions is exothermic. Energy is being released. That is a negative delta H value. So that's an exothermic process. If the attractions between solute and solvent has a higher value, so if delta H3 is greater than delta H1 plus delta H2, then my delta H for the solution will also be negative, will also be exothermic. And conversely, if the sum of delta H1 and delta H2 is greater than delta H3, then the enthalpy for my solution is also going to be endothermic. It's going to be greater than 0. So processes that are exothermic, after you go through that process and you get a delta H for your solution value, processes that are exothermic, so when I have a negative delta H to the solution, tend to occur spontaneously. And that spontaneously means the solute will readily dissolve in the solvent. So if my delta H for the solution, if the solute-solvent interactions are more favored than either solute-solute or solvent-solvent, then that solute will readily dissolve in the solvent, something like sodium chloride. that readily dissolves, and that means the delta H for that solution is exothermic. But that doesn't mean that endothermic solutions, positive delta H solutions, doesn't necessarily mean that it will never dissolve. So a solution will not form if delta H solution is too endothermic, and that too is really, really key. It means that if I have a large positive delta H solution, that's a large positive value, it means the solvent-solute interactions are not very strong, right? So not nearly as strong as the solute-solute or the solvent-solvent interactions. Example here, water, a polar liquid, does not dissolve a nonpolar liquid like gasoline. So I have very strong hydrogen bonds between the water molecules. My solvent IMFs are very, very strong. So any water gasoline IMFs that do form, that exothermic energy is not enough to disrupt the hydrogen bonding between water molecules. So I can't break those water-water IMFs. So that's why water and gasoline and water and any nonpolar liquid don't mix. Oil and water don't mix because it's a polar water and a nonpolar oil. And any water-oil IMFs are not very strong at all. And that's a dipole, induced dipole intermolecular force, and there's not enough energy released from that to break your initial solvent-solvent intermolecular forces. But some endothermic processes can occur spontaneously, and that's because there's another type of energy that we're dealing with. Something like ammonium nitrate is an endothermic delta H for solution, right? But it readily dissolves because when I dissolve a solid into a liquid, I'm increasing what's called the randomness of the solution. I'm dispersing those sodium and nitrite ions throughout that solution. And we measure the randomness of an object of a solution of anything by the term entropy. And we're going to talk a lot more about entropy at the end of the semester in chapter 19. But right now, all we need to worry about is, as far as what entropy means, is that it measures the amount of randomness or disorder of a system. And the process of dissolving a solid into a liquid is always going to result in an increase in entropy. And that's because I'm starting with an organized block of ionic salt that's sitting on the bottom of the container. Those ions, in this example, ammonium and nitrate, are clumped together, are organized, ammonium, nitrate, ammonium, nitrate, ammonium, nitrate. When that dissolves, I now have a random mixture of ammonium ions, water molecules, and nitrate ions. It's more random. So there's an energy value there, and the energy that's released from that process overcomes the endothermic nature of the delta H of the solution. So the overall process becomes favored, becomes spontaneous. And we'll deal a lot more with that in chapter 19. But right now it's important to recognize that it's not just the enthalpy of the solution that matters. We have this entropy value as well. But entropy is only going to matter when I've got a small endothermic value for delta H of the solution. If delta H of the solution is exothermic, it's going to dissolve. We don't need to worry about entropy because entropy is always going to increase when I dissolve a solid in a liquid. Right? And it's just, is that increase enough to overcome a small endothermic value? And sometimes it is, sometimes it isn't. So the formation of solutions is favored by the increase in entropy that comes from the mixing of the ammonium nitrate that overcomes the loss or the energy that's required to disrupt the sodium and the nitrate ionic bond. So another example of mixing is mixing carbon tetrachloride, CCl4, with benzene, C6H14. So we have them in diagram A, we have them in two separate containers. And when we remove the barrier, they do mix together. Right? We have an increase in mixture because now we're mixing two liquids together, but the same rule applies that we saw when we mixed a solid and a liquid. I have a very organized state. I have carbon tetrachloride on the left side of the beaker A, and I have C6H14 on the right side. Now in beaker B, when I mix them together, I have a random jumble of both of those molecules. I have increased the disorder of the system. I have increased my entropy. And again, that will be true for mixing of any liquids. So mixing solids or liquids together will always result in an increase in entropy. And here, the only type of IMF I'm dealing with are London dispersion forces, because these are both non-polar compounds. So the delta H values are very, very small. Delta H1, delta H2, and delta H3 are very small. So much so that delta H3 probably isn't big enough to overcome the sum of delta H1 and delta H2, which means the delta H for the solution is probably going to be endothermic in most cases for mixing two nonpolar compounds. But that increase in entropy is able to overcome that endothermic delta H of the solution to make this a spontaneous process. So even though the enthalpy may increase, I need to add enthalpy. I have a positive delta H value. The overall energy of the system can still decrease when I factor in the amount of entropy that's increased and how that affects the total energy of the system. The solution process involves two factors. The change in enthalpy, our delta H value, which again is simply delta H1 plus delta H2, positive values, plus my negative delta H3, and the change in entropy. And a solution will form unless the solute-solute or solvent-solvent interactions are very, very strong. In that case, the solute-solvent interactions and the gain in entropy are not going to be enough to overcome a super, super strong solute-solute or solvent-solvent interaction. In that case, we have something that's insoluble, and there's not a whole lot we can do about that in and of itself. All right. I think I'm going to leave it right there, and we'll be all set for this section. And I've just got one more section to finish off chapter 13. Thank you very much, everybody.